Good afternoon, students. My name is Darlington. This class is brought to you by Isaac Humanitarian Foundation. Today, we'll be talking about chemistry. Now we shall be looking at the concept of what? Acid. Now, under the concept of acid, we'll look at different pioneers that postulate different definitions in respect of acid. The first we shall look is Arrhenius definition. Arrhenius definition. Arrhenius definition is considered as a classical definition of acid. Paraphrased, it is deemed as a universally accepted definition of acid. According to Svante Arrhenius, a Swedish chemist, an acid is a substance that interacts with water to furnish or produce hydrogen ion or proton as the only positive ion. Examples are tetraoxosulfate acid, H2SO4, 2 hydrogen ion and sulfate ion, hydrochloric acid, giving you hydrogen ion and chloride ion, and a host of other examples. From this illustration on the board, it is evident that the anions vary. Here, in the first example, we have tetraoxosulfate ion. In the second example, we have chloride ion. Now, but here, one ionic species is constant to both equations, which is hydrogen ion or proton. That is the reason in the definition it only embodies hydrogen ion, in that an acid is a substance that interacts with water to furnish or produce hydrogen ion or proton as the only positive ion. However, in the light of new discovery, it was realized that in the definition, Arrhenius stated interact with water, but in his equation, water is not embodied, which shows that there is a defect with his equation. And of course, there is a defect associated with the definition. In the light of new discovery and extensive research conducted by modern chemists, this definition, as carefully propounded by Svante Arrhenius, has been refined and restated as an acid is a substance that interacts with water to furnish or produce hydrozonium ion, or oxonium ion or hydronium ion as the only positive ion, as exemplified as follows: H2SO4 plus H2O, water, we have it to be H3 plus and SO4 2 minus. We put 2 here and put 2 here. Now, hydrogen here is 4. This is 2 times 3 here, 4, plus this 2, 6. 2 times 3, 6. Sulfur here 1, sulfur here is 1. Oxygen here is 4 plus 2 here is 6. Oxygen here is 4 plus this 2, 6. Now, HCl plus water giving you hydrozonium ion and chloride ion. This is called hydrozonium or hydronium or oxonium ion. From this second equation, it is crystal clear or evident that water interacts with the hydrogen ion. So ironically, this above equation can be translated as hydrogen ion plus what? Plus water. 2 hydrogen ion plus water. giving you 2 hydrozonium ion, This second equation, this first equation, second equation. The second equation can be translated as hydrogen ion plus water. This will give you hydrozonium ion. So this implies that the water, according to a result of experiment, interact with hydrogen ion to yield a new species, which is called hydrozonium ion or hydronium or oxonium ion. Therefore, when inquired in external exams like WAEC, WAEC SSE, WAEC DC, NECO DC, you have to define acid as a substance that interacts with water to produce hydrozonium ion as the only positive ion. That is definition by Arrhenius. The second definition is called Bronsted-Lowry what? Bronsted-Lowry definition. G.N. Bronsted of Denmark and T.M. Lowry of England independently propounded a definition of acid. According to this definition, they stated that an acid is a what? A proton what? Donor. A base is a proton what? Acceptor. Is a proton acceptor. Now, note that all Arrhenius acids are Bronsted-Lowry acid. But all Bronsted-Lowry acids are not Arrhenius acids. Similarly, all Arrhenius bases are Bronsted-Lowry bases, but all Bronsted-Lowry bases are not Arrhenius bases. And one advancement of Bronsted-Lowry definition over Arrhenius definition is that Arrhenius definition embodies reaction that occurs principally in aqueous medium or aqueous matrix, that is in water. But in Bronsted-Lowry definition, it encompasses reaction that occurs both in aqueous matrix and non-aqueous medium, as exemplified in the reactions on the board. Now, this is X hydrogen ion plus water, giving you what? H2O plus H2O, giving you hydrozonium ion and hydroxide ion. Now, we take this as acid 1, we take this as base what? 1. We take this as acid 2, and we take this as base 2. From the diagram on the board, water is made up of is an integration of hydrogen ion and hydroxide ion. Of course, if you aggregate both, you have H2 what? You have H2 what? O. Now from here, if you remove one H from here, of course I left it OH. This is the OH here. Now, if you remove the H interact with this man, as we have said in preceding section, to give hydrozonium ion. The residual OH is liberated as product here. Now, if you look at this, based on pivoting on Bronsted-Lowry definition, water here, this particular water here, behaves or functions as what? Acid. Why this water here behaves or functions as what? A base. On the right hand side of the equation, hydrozonium ion here has 3 hydrogen ions. Of course, it would relinquish one hydrogen ion to hydroxide ion. When it relinquishes one hydrogen ion, you are left with what? 2 hydrogen with water, giving H2O. This. And the hydrogen ion interact with this man to give you this water. From this illustration, it is crystalline that hydrozonium ion here is an acid because it relinquished a proton or hydrogen ion to this hydroxide ion. An hydroxide ion here is a base, but here we'll tag it as what? Base 2. Now, there is a term we refer to as conjugate. Conjugate literally means marriage. Now, here we pair an acid and a base in terms of a conjugate relationship. Here, this acid and the base will be paired together. This acid and this base will be paired together. Now, we report it as, look at how we report this. You report it as conjugate base of an what? Acid. Conjugate base of an acid. That is, hydroxide ion is a conjugate base of the acid water. Hydroxide ion, that is the base 2. We report as the base of an acid. So hydroxide ion is a conjugate base of the acid water, whereas hydroxide ion is a conjugate acid of the base water. From here in Arrhenius never deemed water as an acid, but in Bronsted-Lowry's definition, water is considered as an acid, and that explicates my preceding statement that states that all Arrhenius acids are Bronsted-Lowry acids, but all Bronsted-Lowry acids are not Arrhenius acids, as evident here. This is water here is an acid, as you can see on the diagram. But in Arrhenius definition, water is never an acid. Rather, it is a medium in which the reaction happens. But here now, since here in this definition, you can see water behaving as an acid, which means in Bronsted-Lowry, water is an acid. But in Arrhenius, water is not an acid. So here, hydroxide ion is the conjugate base of the acid water, and hydroxide ion is the conjugate acid of the base water. So water has a dual behavior. Water has dual behavior in that it could function as an acid here or as a base here. Another example to clarify the definition is ammonia. Ammonia plus water to give this NH4 plus and hydroxide ion. Aqueous, liquid, gas. Here, water relinquishes. Recall I stated that water is an aggregation of hydrogen ion and hydroxide ion. In that, water will relinquish one hydrogen ion or a proton to ammonia. Ammonia has three hydrogen atoms, giving you NH4 plus. While the residual OH ion is liberated as hydroxide ion. From this diagram, from this equation of reaction, it is evident that water behaves typically as a Bronsted-Lowry acid. Therefore, we label it as acid 1. Ammonia accepting the hydrogen ion relinquished by the water molecule is considered as a base. That is, based on the definition, a proton acceptor. Therefore, we designate this as base 1. Coming to this right hand side of the equation, ammonium ion relinquish a hydrogen ion, give off a hydrogen ion to this hydroxide ion. Therefore, it functions as an acid. Here, this man accepts the hydrogen ion from this man to form what? Water. Therefore, it functions as a what? As a base. Recall I told you that the term conjugate literally implies a marriage. In that, here, we will graft that concept into chemistry to mean a relationship or interlink between a base and an acid. That is, base-acid relationship. In that case, instead of saying base-acid relationship, we use the term conjugate. Now here, this This ammonium ion is a conjugate acid of the base ammonia. A conjugate acid of the base ammonia. Whereas hydroxide ion is a conjugate base of the acid water. That is for Brostolori's definition. Then the next one is strength of an acid. Strength of an acid. Strength of an acid. Acid may be considered, may be grouped into two. May be grouped into two categories based on their strength. We have what is known as strong and weak what? Strong and weak acids. Strong and weak acids. What is a strong acid? Strong acids ionize completely in aqueous medium. Ionize completely in aqueous what? Ionize completely in aqueous medium. Now, we differentiate between two forms of acid. We have what is known as the oxo acids, and we have what is known as the hydrohelic acids. Now, what is oxo acids? An oxo acid is one that incorporates an oxygen atom attached to a hydrogen atom. For instance, this is an oxo acid, H2SO4. This is an oxo acid that incorporates an oxygen atom linked to a hydrogen atom. Then we have other examples, such as oxochlorate 1 acid, HClO, is an oxo acid because it incorporates an oxygen atom. Then we have the second class of acid, which is called hydrohelic acids, which embodies a class of acid incorporating a halogen atom. In that we have hydrochloric acid, hydrobromic acid, hydroiodic acid. These categories of acids are subsumed in hydrohelic acid. So note the difference, oxo acid and hydrohelic acid. Now based on strength, strong acids ionize completely in aqueous medium. Now there is a simple rule I call the golden rule, with which I can conveniently and with ease recognize if an acid is strong or weak. Now this simple rule is this: if number of, I call it golden rule, if number of O atoms, that is for what? Oxo acid. Golden rule for oxo acids. If number of O atoms exceed, number of H atoms by 2 or more, acid is said to be strong. Acid is said to be what? To be strong. Some students, when you ask them if an acid, if they could recognize whether this acid is strong or weak, they will tell you strong, some will tell you weak. Why are they indecisive to know if an acid is strong or weak? They only know an acid, they will ask them, identify if this acid is strong. They will tell you it's strong. If you ask them, they will tell you it is because it ionized completely. But the question is, how do you know if an acid ionized completely? For example, let me use a strange acid, nitric acid, HNO4. I guess you might not have had this. HNO4, we have HNO, HNO2, HNO3, and HNO4. We call this nitric acid or tetraoxosulfate 5 acid. Now, in looking at this acid, when you ask a student, HNO4, is it a strong acid or a weak acid? They are often indecisive and always have a vague memory of whether this is strong or weak. Some will tell you strong, some will tell you weak. Now, the simple rule is this. Look at this simple rule, which I designed. If number of O atoms exceed number of H atoms by 2 or more, acid is said to be strong. So with this simple golden rule, you can decide if an oxo acid is strong or not. Okay, let's come back to this strange acid which I delineated on this board. Now for HNO4, the number of O atoms here, number of O atoms as evident in the formula is what? 4. The number of H atoms as reflected in the formula is what? 1. Now the difference between the number 4 minus 1 equal to what? 3. The rule says 2 or more. 3 is greater than 2, which means HNO4 is a strong oxo acid. Then look at HClO, oxochlorate 1 acid. Now the number of O atom is 1. The number of H atom here is 1. There's an invisible 1 here. So in that case, the difference is 0. So which does not comply with this. So in other words, HClO is a weak acid. HNO4 is a strong acid. So if we are not talking about examples of strong acid, so we are looking at Arabic numeral 1. We have oxo acids. Oxo acid, e.g. H2SO4. Please look at it again. 4 oxygen atoms, 2 hydrogen atoms. The difference here is what? 2. H2SO4 is a strong acid. Then HNO4, pernitric acid. Old name, IUPAC name, tetraoxosulfate 5 acid. Is this strong or weak? We have number of O atom 4, number of H atom 1. Difference is what? 3. Therefore, it's a strong acid. Then we have another one, HNO3. This is nitric acid or triazole-35 acid. There, number here is 3. Number here is what? Number here is 1. The discrepancy between the two, between the number of O atom and H atom is what? Exactly 2, which is in concert with the rule. Therefore, HNO3 is considered as a strong acid. Please, this is tetraoxosulfate 6, NO4 minus. NO4 minus. So nitrogen here is X plus 4. Oxidation state of oxygen is minus 2, equal to the overall charge, which is minus what? Minus 1. So X here, this is plus 4 times minus 2, we give you minus 8 equal to minus 1. X equal to minus 1 plus what? 8, which will give you plus 7. Therefore, this is tetraoxonitrate 7 acid. Please, there is a common error committed by students. They will tell you hydrogen tetraoxonitrate 7 acid. That is very, very erroneous. That is wrong. It is, once you mention the acid, then there is no point saying hydrogen. The acid there connotes the word hydrogen. The word acid at the end of the name connotes the word what? Hydrogen ion. So there is no point saying hydrogen. Hydrogen tetraoxonitrate 7 acid. No, it is tetraoxonitrate 7 acid. Tetraoxonitrate 7 acid. Why this one is trioxonitrate 5 acid? They are all strong acid. Then 2. For example of hydrohelic acid, we call it hydrohelic what? Acids or hydrogen halide acid. Hydrogen halide what? Hydrogen halide acid. Example gratia is hydrochloric acid, hydrobromic acid, and hydroiodic what? Hydroiodic acids. These are examples of strong hydrogen-halide acid or hydrohelic acid and strong oxo acids. They ionize completely in aqueous matrix to furnish ions. We talk about B of these. Weak acid. Weak acids ionize incompletely or partially in aqueous matrix or in water to produce fewer number of ions. Examples are Roman numeral 1. We have oxo acids. The rule, remember the rule for strong acid. If number of O atoms exceed number of H atoms by 2 or more, acid is said to be strong. On the contrary, if number of O atoms is equal to number of H atoms or is less than 2, the acid is designated as weak acid. Example of weak oxo acid: carbonic acid or trioxocarbonate 4 acid. The difference here, this is 3, 2. The difference is 1. The rule says if it is less than 1, if it is less than 2, then it is a what? A strong acid, is a weak acid. This is 3, this is 2. The discrepancy here is 1. Therefore, this carbonic acid is considered a what? A weak acid. Then, hypochlorous acid or oxochlorate 1 acid. HClO, the difference here is this 1, 0. Of course, there is no difference. That means this is a typical or an archetype of a what? A weak acid. A typical example of a weak acid. Then, other example, phosphoric acid, H3PO what? H3PO4. Then look at it, this is 4, this is 3. The difference here is 1. Therefore, it is a what? A weak acid, etc. Then, Arabic numeral 2, we have hydrohelic acid. The only hydrohelic acid we have as weak acid in this category is hydrofluoric what? Acid, HF, hydrofluoric acid. It is one of the weak acid among the hydrohelic acid. Then another third category of weak acid we have that sometimes seems very surreal and strange to most students and teachers is acid in which H atom is linked or bonded to atoms other than O and what? A halogen. I repeat, an acid in which a H atom is bonded or interlinked with atoms other than O atom or a halogen atom. For example of that is hydrocyanic acid. This man, that is, if you look at here, cyanide ion, Cn- is interlinked with a hydrogen ion. You can see that here, that means that the hydrogen ion is not linked or bonded to a O atom or a H atom. In that event, hydrocyanic acid is a weak acid. Another example, you might be so surprised, is hydrosulfurous acid, H2S. Yes, some will tell you hydrogen sulfide. Yes, then the H2S has an ambiguous term. Now this ambiguity is dissolved by indicating the state symbol G, H2S, AQ. Now look at these two. Look at the clear cut between the two compounds. In the former example, you have the state symbol as gas. In the latter example, you have the state symbol as aqueous. What does that connote? It connotes that this is hydrogen sulfide gas. This is a gas, hydrogen sulfide. Why this one is articulated as hydrosulfurous acid, not hydrogen sulfide acid. Hydrosulfurous what? Acid. So this is an acid. So a weak acid. These are the 3 examples of weak acid we have. Oxo acids, hydrohelic acid, e.g. HF, and hydrogen cyanide, and what? Hydrogen sulfide. These are the 3 categories of weak acid we have. Then we go to the next part, which is we are still talking about the strength of acid. Then we have the 2, which is concentrated and dilute acid. A concentrated acid is one that contains large amount of the acid relative to water, whereas a dilute acid contains less amount of acid relative to water. Literally, concentrated acid contains more acid and little water, whereas dilute acid contains less acid and more water. Now, that is for the strength of acid. Now, we'll talk about the sources of acid. We have 2 sources of acid. We have what is known as kinds of acid. We have organic acid and we have inorganic acid. Now, what is organic acid? I believe you will all acquiesce in the fact that organic has to do with material gotten from plants or animal kingdom, or material or substances. So organic acid refers to acids that are derived from plant and animal materials. Now here we look at the different classes of organic acid and their respective what? Sources. Organic acids and what? Sources. Remember, we are talking about the types of acid. So organic acids, we have the first one, which is ethanoic acid. Ethanoic acid is gotten from what? Vinegar. Then we have formic acid. Formic acid is gotten from ant sting. Sometimes when you are being stung by soldier ant, the nasuit soldier. We have 2 kinds of the soldier ant. We have the nasuit soldier, we have the mandibulate soldier. Of course, the clear cut is evident in the structure and shape of their what? Of their mouth parts. One has a powerful and a strong mandible, as in the case of the mandibular soldier. Then we have the nasuit soldier, which has a rostrum through which it can eject a poisonous chemical into the body of the prey, leading to a total discomfort. Now, when you are stung by ant, by the nasuit soldier, all you need to do is, since the ant sting is made of acid, all you need to do is, some people will tell you, you apply an alkaline. Don't ever try that. If you apply an alkaline, it will definitely consume the skin, because of the fact that alkaline is caustic. So what you need to do is to bait with what? Soap. Of course, soap is developed from what? Alkaline. So whenever you are stung by ants, you bait with what? With soap. Soap being made of alkaline will neutralize the acidity of the toxin injected into the body. So formic acid is coming from ant sting. Then we have another one which is called the oleic acid. Oleic acid. Oleic acid is coming from palm oil or palm fruits. Oleic acid is coming from palm fruits. Then we have ascorbic acid, which is gotten from vitamin C. We have citrus fruits, which is gotten from orange, Latin or botanical name citrus sinensis. Those are the class of what? Organic acid we have. Then on the other hand, we have inorganic acids. Inorganic acid is otherwise called mineral acids, as these acids are synthesized from materials in the laboratory. As a consequence, we refer to them as inorganic acid or mineral acid. Examples are tetraoxosulfuric acid, H2SO4, trioxocarbonate 4 acid, H2CO3, tetraoxonitrate 7 acid, HNO4, oxochlorate 1 acid, HClO, that is hypochlorous acid. Then we have oxochlorate 5 acid, HClO4. Then we also have another one which is called hydrohelic acid, hydrobromic acid. Then we have the caro acid. Then we have the oleum, there is an H2S2O7. All these range of acid as are delineated are subsumed into what? Inorganic acid or mineral acids.